Okay, so before moving on to this problem, yesterday some students from other batch they were asking. Uh, so we have seen that error has two components. One is coming from truncation error, and other is coming from round off error. So this round off error, it is a computer related. Okay, it's a hardware related, computer related, software related. And this truncation error is what we do trailer series. Okay. So we have seen that say forward difference is of the order of delta x, backward difference is of the order of delta x or delta t. Central difference is of the order of delta x square and so on and so forth. So by using proper delta x, we can increase, suppose we decrease delta x, then it is obvious that at very small delta x, FD, BD and CD, they may be all equal. So by reducing delta x, you can reduce the truncation error. But when you go from 0.1 to 0.01 and 0.001 or so and so forth, now if you do calculations, zero point 0.1 multiplied by zero point 0.1 say, or the sum of that or division of that. So any operations you do, now you will see that the significant, this decimals, they start changing. So you can see some changes here. So these round of errors, so as you decrease this round of errors, they start increasing. Okay. So the pattern of error is something like that. So this is a pattern of round of error. And the other one, this is a pattern of truncation error, where this is, you can say your delta x, and this you can say error. So as you decrease delta x, you see that there is a decrease in the truncation error, but increase in the round off error. If you increase delta x, then you see that the round off error reduces, but the truncation error goes on increasing. Okay. So there is a limit from both the sides, which is a optimal limit. So at this delta x optimal, what do you see that your truncation error as well as your round off error, they are sort of compromised, neither high, neither low, like that. So there is a optimal value of delta x or delta t for which the truncation error and round off error, they will be of minimal nature. Okay. Not exact minimal, but optimal, you can say, where we can make a compromise between both. So we give importance to both. So here both are important. Here, if you go below that, then you will get less importance of to the round off, I mean, round off error. So suppose, what do you mean by that grid independence is that suppose your first grid is here, nth grid, then might be your twice n grid is coming here, approximately here, and your twice of twice n grid is coming here. So what you'll see that n to 2n, maybe there are variations, or this 2n, rather than saying 2n, this can be twice of 4n, twice of 4n, and 2n is somewhere near itself. No, it is a log graph. So it is near only. So here you will see that near this point, these two grids will match. Twice n and 4n grids, they will match. So we'll say that sufficiently, it is sufficient for 2n grid to have minimal truncation error and round off error, and we will not go further. It also may be possible that your first grid you might have taken here, and then your second grid 2n and third grid 2n. So you might get error in all the simulations, n, 2n and 4n. So you might get error in all this zone. Okay, so if you are getting errors in all these zones, then you have to shift here. From n, you will have to shift to say something like n by 2, and likewise maybe somewhere here n by 4. So that finding out this optimal is nothing but called as finding out an optimal value of delta x and delta t. Okay. Is respectively called as grid size and time step independence study. Okay, so let us move on to our problem. Yesterday we started with this problem, 1D and steady state. And this is a fin equation. So we have to draw a geometry of that fin. Okay. the rectangular fin is given, and we have to divide this into, since this is a 1D region, we'll divide it into I number of points. Okay. So we'll divide this into n plus 1 number of points, starting from 1 to, so say this is 1 point, second point, the last point is n plus 1, and before that it is n point, n minus 1, like that. And we can designate them as I plus 1, and I minus 1 in a general notation. According to this problem, at x is equals to 0, you have been given a value of temperature, that is Tw, and here the value x is equals to 0. And the question is, find out T2, find T2, T3. Okay. So T1 is equals to Tw, T2, T3, T4 up to Tn plus Tn plus 1 or Tn. Okay. So how do we do it? And here I and I plus 1 and I and I minus 1, they are separated by a distance delta x. So uniform grid is considered, and this is a total length L, total length L. So depending on the number of points you want, so you will divide this into a different region. So suppose I want 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So 9 means I need this 1, 2, 3, 4, 5, 6, 7, 8 regions. Okay. 8 delta x's I need. So how I can get delta x? So delta x is equals to, so solution procedure is delta x is equals to, first you have to calculate the grid parameters. So grid parameter is delta x is a grid parameter. Delta x is equals to length divided by number of points n, means n plus 1, that is n plus 1 minus n minus 1, that is n. Okay. So there are 9 nodes but 8 delta x's. So delta x is equals to L divided by n. So you will get a delta x value. You will get some value here. If L is given, n is given, you can get delta x. And that will be our useful parameter here. Now, what do we do? We use, we want this to be discretized, del 2t, dx2, okay, minus hp a ti minus t infinity, okay. So ti means, I'll just write here itself, this whole at I is equals to 0. What about n? What about n here? What about n here?
Sir, all at the same time step.
But is it a n or n plus 1?
Sir, n plus 1. No, n, sir.
So all are known.
Yes, sir.
Then what is to be unknown?
Oh,
Which one is unknown?
so the time step also will be n plus 1 then.
Hmm?
Sir, so the time step
Yes.
you're saying will be n
Yes.
plus 1. Okay, sir.
Yes. Isn't
Fine.
it? Because if all are
Okay.
known, then what is to be find out, isn't it?
Sir,
So
so
there is no time there is no time derivative here, but it is essentially, it means that these are simultaneous equations. If you use, so what, suppose now I want to discretize this I. Okay, let us forget about time. So which method I will use here? So we know that for second order derivatives, central difference, isn't it? And here there is no derivative term, only value term. So we'll use the value at that ith point. So central difference scheme for d2 t dx2 is t I minus 1 minus twice t I plus t I plus 1 divided by delta x square, isn't it? This is done. Minus this HP and K. If these are given values, this can be a constant. So this will be a number T. So T at I, and that minus becomes plus HP KA T infinity equals to 0. Okay. Now if you arrange this, so we can arrange this into known and unknown, and we can break similar parameters here. So after arranging this, Ti minus 1 minus 2 minus 2 uh, plus HP by K Ti, isn't it? Plus here delta x square plus Ti plus 1. Okay. And this thing is a known value. T infinity is a known. Okay. It should be given. So known value. This you can write minus HP delta x square divided by Ka T infinity. Okay. So we have now written in a consistent manner. Let us represent this term by some constant values since they are known values. So minus 2 plus, say we'll write B, capital B, Ti plus Ti plus 1 is equals to minus B T infinity. Okay. So this is the consistent equation for this particular, this is a this finite difference equation. Okay. For this particular derivative Gauss equation, ODE, or you can say PD also. Okay. So
Sir,
now this, uh,
So that delta x square term,
Hmm.
can you please explain that, sir? In the above step.
You are multiplying by delta x square. Okay.
Yes, sir. Okay, sir. Thank you.
So this is the equation. So this equation is for I plus 1. Okay. And what are I plus 1, I minus 1? This, and this. Anything can be I, isn't it? This point is also I, and next point to that I is I plus 1, and before that I minus 1. Okay, if somebody is getting confused, I doesn't mean that this point only. I is a general point. Okay, point under consideration is a I point, and before that point is a I minus 1 point, and after that point is a I plus 1 point. Forward point and backward point, we can say. So this is in terms of the point under consideration, before and after that point values, and this gives a general uh, you know uh, term, general difference equation. Now here, if you see the stencil of this particular scheme, what are these elements? I minus 1, I plus 1. So stencil is this only, isn't it? So in terms of stencil, your finite difference equation will come. If in your stencil I plus 2 term was there, then that term should come here. But since we are taking central difference, where in central difference I minus 1 and I plus 1 values are only coming. But we can have a other order of accuracy central difference term, and it may have other terms also possible. So this is a equation we got now. Now we have to write this equation at every I. Okay. So from that figure, we see that from this figure, at I is equals to 1, what is the t value? T is nothing but T1, isn't it? T1 is equals to Tw. This is a given. So this is a boundary condition. At I is equals to 2, at I is equals to 2, this equation you have to apply. This equation number 1. So from equation 1, I means 2 minus 1, 2 minus 1 minus 2 plus B, T2 plus T3 is equals to minus B T infinity. Okay. So this is nothing but T1 minus 2 plus B T2 plus T3 is equals to minus B T infinity. So from this first equation, T1 is known, T1 is Tw, Tw is known, Tw minus 2 plus B T2 plus T3 is equals to minus B T infinity, which is nothing but equals to minus 2 plus B T2 plus T3 minus B T infinity minus Tw, isn't it? So I'll write this equation as I'll write this equation as 1. A, I'll write this equation as B prime, B1 prime, and B2 prime, or I write this A prime, B1 prime, B2 prime. We have either this equation or this equation. This is also possible, this is also possible. May not write, need to write. I'll tell you later on. Don't get confused. Let us go for one only. Okay. Then it is okay. At I is equals to 3, next point, this I3 point. So again, at I3, so this equation, if you see this equation, equation number 1, where I is running from 2 to n, where I is running from 2 to n. Okay, so for I is equals to 3, there is no boundary condition. So this equation only, equation number 1 is there. So from equation number 1, again, T3 minus 1 minus 2 plus B, T3 plus T4 is equals to minus B T infinity, isn't it? So this is T2 minus 2 plus B, T3 plus T4 is equals to minus B T infinity. And this is C prime. Similarly, at I is equals to 4, T, so you see, when I is equals to 3, this is 2. When I is equals to 4, this should be 3. We will get similar pattern of the equation. Central value is T4 plus 1 increased value T5 is equals to minus B T infinity. You say this is D prime. Similarly, I is equals to 5 T4 minus 2 plus B T5 plus T6 is equals to minus B T infinity E prime. Similarly, if you go I is equals to N, then this should be T n plus 1, isn't it? Minus 2 plus B n minus 1, isn't it? This should be n minus 1, and this should be Tn plus Tn plus 1 is equals to minus B T infinity, and this is, so up to that, let me write this is n prime. So up to n we got, up to n means we got up to this last point, interior point, last interior point. These are all interior points. So remember that this equation which we get, that is only for interior points. At boundary points, there are boundary conditions. Okay. Now let us look at I is equals to n plus 1. At I is equals to n plus 1. What do we have? Del t del x is equals to 0. Now this is a derivative term. So we need to discretize it at I is equals to n plus 1. So this has to be discretized at del t del x at n plus 1 should be equals to 0. So what will do? Which expression will you use? which expression will you use?
Backward difference.
Backward difference. Okay. So simplest backward difference of order, backward difference of order of accuracy delta x is there. Also, it is possible that we can get a backward difference with delta x square accuracy, isn't it? So for BD of order delta x, we have for backward difference which having order of error accuracy delta x, we can write this in terms of t uh, n plus 1 minus Tn divided by delta x is equals to 0, and delta x Tn plus 1 minus Tn 0 into delta x 0. So t at n plus 1 is nothing but equals to Tn, and this is our n plus 1 prime equation. Okay. Say I want to now use another equation. So for say for delta backward difference with higher order accuracy, we wish suppose higher order accuracy delta x square, then we have an expression dt by dx can be written as equals to I'll simply write here. The expression is price t n plus 1 minus 4 Tn plus T n minus 1 divided by twice delta x. This is also an expression. You can use this or either of these two. You will get, this has to be 0. So you get 3Tn plus 1 minus 4Tn plus Tn minus 1 is equals to 0, and this n minus 1 will be the term, known term, okay, previous term. We can write this also. So you can arrange this in ordered manner, Tn minus 1 minus 4 Tn plus 3 Tn plus 1 goes to 0. This is also possible equation, but we'll go for this. Now, if you see all these equations, I can combine these equations. So I can start with this equation a prime, then I can start with b1 prime. Okay, I'm starting with this, and all other equations, all these equations along with this third equation. So I can combinedly write these equations here as a matrix. So T1 is a known value TW. So I can write that known value. So say known value is there, suppose. So that known value, say it is equals to alpha. So I can write alpha, and then from the second equation, this say T1 is already alpha, so we'll write alpha, again alpha, and then second term is 2b, and third term is 1. Okay. The next equation, if you go to this equation coefficient is 1, T2 coefficient is 1, then central coefficient is minus 2 plus b, and then third is like this, again 1 minus 2 plus b, 1. Okay. If you keep on adding, you will get terms like this. A matrix term. And here, this will be a term related to T1, this T2, T3, T4. Likewise, you should go up to Tn plus 1. So at Tn plus 1, we have Tn plus 1, we have Tn value, and that or we can write it as Tn plus 1. So Tn plus 1 minus Tn. So minus 1, 1. Okay, here will be a Tn. For n we have n minus 1 and like that. So minus 2 plus b, 1, 1. Okay. So you see this have a nice arrangement here. All these diagonal entries have some nice arrangement, and subdiagonal elements are there. Rest of the elements, they are 0, isn't it? Rest of the elements, they are 0. And here also there are many zeros. Likewise, there are terms. Okay. And this right hand side will be equals to, this is T1 alpha T1, means T1 is so coefficient of T1, not alpha, coefficient of T1, this equation you can write it as T1, coefficient of T1 is 1, coefficient of T1 is 1, Tw is alpha, so coefficient of T1 is 1, so here you will have to write 1 only. Coefficient of T1 is 1, coefficient of T1 is 1, T1 is equals to Tw, so Tw. Okay, this matrix multiplication Tw. This T1 minus 2 plus b T2 plus T3, which is nothing but equals to minus b T infinity, isn't it? Second, this one, this equals to T2 minus 2 plus b T3 plus T4 is equals to minus b T infinity. So everywhere minus b T infinity is there. Here also minus b T infinity. And in the last equation, Tn plus 1 minus Tn is equals to 0. So this is a matrix obtained from these tick marked equations. But suppose I don't want to, because since this is a boundary point and this is a boundary point, they can be easily calculated. So they may not be considered in a this matrix, and you can get simply a matrix of reduced size, a matrix of reduced size like this. And this term which was there as a 1, you will have to here -1 and reduce all this. So you see, we have reduced the matrix size. Okay. So that T1, sorry, 1 is TW. T1 is equals to TW. So T1 goes here. T minus T1 means nothing but TW, given value. And here, you have to remove this also. So so we got reduced to this form. Okay. So now this is T2. This is known, and you get Tn. Once you get Tn plus 1 is known from this, the second equation, last equation, isn't it? This equation will give you n plus 1 value if Tn is known. Tn can be known from this equation. Okay. So there are, need not to deduce that. You can solve that previous matrix also and this matrix also. But solving this matrix is easy compared to the previous matrix, because here size of the matrix get reduced since boundary conditions are given. So we can use this form. So this form is a Ax is equals to B form, isn't it? Matrix form. Ax is equals to B form. Now to solve this matrix, methods of solution of matrix, we know that there is a direct method, isn't it? We know that there are iterative methods. That direct method is a Gauss elimination, and iterative we have a Jacobi and Gauss Seidel and Gauss Seidel successive or relaxation or under relaxation. Okay, Gauss elimination, we have one, one specific method. Now here you see, so these are the methods. So you can use direct method here. So in direct method, what you'll have to do, you have to reduce these terms, you have to convert these terms in terms of zeros, this term, okay, so that you get finally a term here which will be expressed in terms of these values, and you get backward substitution and you obtain the values, isn't it? That is what we are doing. But already there are some zeros. When you apply Gauss elimination, there are already zeros. Okay. So if you write a generalized algorithm, general code, then in the general code, it will be always subtracting these zeros, isn't it? Because in general code, you do not know that where the zero is there or not. Okay. A general procedure you will follow, in that you will try to reduce, check, reduce like that. So if you use Gauss elimination method, so sometimes these zeros may become some numbers, and you may unnecessarily compute and do computations. Okay, so there is a method to go around this Gauss elimination method. It is a type of Gauss elimination method in a direct method. A type of Gauss elimination Gauss elimination, but specific Gauss elimination, that is called as Tdma. That is called as Tdma. Tridiagonal, the long form is tridiagonal. TD, this stands for TD, matrix algorithm. Matrix algorithm or Thomas algorithm. Thomas algorithm. Now here tridiagonal, this term is coming from the nature of the matrix. So here you see this terms, this this diagonal is called as main diagonal. Okay, and there is another diagonal here. If you notice, this is called as upper diagonal. This subdiagonal or upper diagonal, and there is another diagonal at the bottom, which is called as lower diagonal. Okay, so there are three diagonals: number one, number two, number three. That is the reason it is called as. Therefore, it is called as tridiagonal. And in engineering problems like this problem, we get a tridiagonal matrix. Similarly, in many other cases, you will get tridiagonal matrices. So to take the advantage of this direct method for small size of the problem, and to circumvent the computation needed in G, Tdma is developed so that number of computation needed in Tdma will be always less than Gauss elimination method, and that is given by Thomas, a scientist named Thomas, and it is popularly called as Thomas algorithm or tridiagonal matrix algorithm. Okay. And you can use other methods also, like iterative methods, Jacobi, Gauss Seidel, and Gauss GSSR. Already we have seen how to do solution with this, and you can obtain these values. Okay, these values T2, T3, T4, and Tn. Okay, let us look at a tridiagonal matrix algorithm. So we'll consider an example, and by that example, we'll try to get into this Tdma. Okay, so let me write, let the matrix is like this. So I can write B1 as element, C1, and rest of the terms 0, A2, B2, C2. So this, you can see the consistency in the notation. A3, B3, C3. Likewise, you can go up to AN minus 1, BN minus 1, and Cn minus 1, and you can go up to Bn and AN. Okay. So you see some tridiagonal format in this way. And let us represent this x1, x2, x3 up to xn minus 1 and say xn also. And these d1, d2, d3, dn minus 1 and dn. So this is more like a Gauss elimination only. So what do you do is first row is chosen. First row is chosen as pivot and multiplied by A2 B1, A2 B1 and subtracted and subtract from second row. Okay, so this is the first row and second row. You choose a pivot and multiply it by A2 B1 and subtract from the second row. To eliminate A2. Our objective is to eliminate this. Okay. So after doing this, what do we get is B2 is equals to B2 minus A2 B1 C1. And similarly, this D2 will be equals to D2 minus A2 B1 D1. A2 B1 D1. Okay, so B2 is expressed as B2 minus A2 B1 C1. Okay, A2 gone, A2 got eliminated because we have multiplied such a way that A2 will be subtracted, eliminated. Now we move on to next row here, and we would like to eliminate this considering this equation as a pivot equation and eliminate so now this second equation is it should be a modified equation, okay, with eliminated this one. Once we eliminate this, then only this pivot equation, okay, after elimination. So modified equation. So second row of matrix with modified elements with modified equation is chosen as pivot to eliminate A3. And after doing that, you again get B3 is equals to B3 minus A3 divided by B2 C2, and D3 is equals to D2 minus D3 is equals to D3 minus A3 B2 D2. Okay. Now what do you do? Again, this modified equation, you make it as a pivot and then eliminate other terms. Keep on doing up to that, you get a sort of pattern. Okay. So what is this pattern is? Okay, repeating this procedure, you get repeating the procedure, we get a generalized version. So Bi is nothing but equals to Bi minus Ai divided by Bi minus 1 and Ci and Di is equals to Di minus Ai divided by Bi minus 1 Di minus I minus 1, isn't it? I minus 1 Di minus 1. And where this I is running from 2, 3, isn't it? 2, 3 up to n. And unknowns are now determined. So after you get this thing, the finally what do you see is that you will get a this form. After eliminating all the subdiagonal elements, you will get this is your, suppose this is your B1, then you got B2 prime, this is a new B2, then you will get B3 prime. So likewise you will get Bn prime with these values C1 prime, C1, C1 prime, C2 prime, C3 prime, like that. All other values here are zeros. So what do you see is that x1 to xn, now we got a, reduced matrix, isn't it? We got this lower triangle 0. So now we can do a back substitution. Okay. So we find these unknowns by back substitution. So once this got reduced, we find by back substitution, and the formula for that you can write unknown xi's can be not apostrophe xi's are determined, can be determined by back substitution. Okay. So last term xn will be equals to bn dn divided by dn divided by dn divided by bn okay, and then xi will be equals to di minus ci xi plus 1 divided by bi where I is running from back. Okay, so n minus 1, n minus 1, n minus 2 up to 1. Up to 1 means that up to this 2, up to this 2. I mean, here it is 1, so we'll write 1 here. In case of our problem, we had a 1, 2. So up to 1. So from this example, we are running from xn minus 1. So for first case, it is a simply this relationship. Now this is 0. So xn is equals to dn. This is the d value, dn divided by bn. And here this value is 0. So this value xn minus 1 is calculated as like this: xn minus 1 is equals to dn minus 1 minus cn minus 1 is equals to x into xn divided by bn minus 1. That will be an expression for n minus 1. Similarly, if you go back up to x1, you can use similar form of equation, but at x is equals to n, I is equals to n, you have to use this equation, but I is equals to n minus 1, n minus 2 up to 1, this is the equation. And you can get all the values of x. Okay. So first you have to find out B2, D2, that is B2, B3, B4, B5, D1, D1, D2, D3, D4, D5 up to Dn. And then once you know Dn and Bn, then you know also the Cn, also Ci's are known. So with these known values, you can simply plug here and you can get the solution. Okay. So you don't have to do Gauss this pivoting and dividing and this thing. You have to use this equation only. Simply use these equations. Use this equation means essentially this is the equation. This is a generalized equation. So use a for loop, and this is another for loop. So for I is equals to 2 to n, you just simply keep on calculating di's. So for I is equals to 2 up to n, you calculate bi and di's. Okay. And then for I is equals to n, you I at I is equals to n, or for I is equals to 1 to 1, you keep on calculating xi's, and for at I is equals to n, you calculate xn is equals to whatever dn divided by bn. Dn and bn will be obtained from these values for loop. So you will get xn, and then xi values can be calculated from this for loop. Okay. So simply you have to keep on calculating this. There is no matrix multiplication or row change or like that, as it is with Gauss elimination. Okay. So your algorithm will be very straightforward. So let us consider as an example.
Sir, we have another class, sir.
Okay, time is over. Okay. So I'll give you some matrix, and you will have to solve this matrix as an homework using Gauss elimination. Okay. So I'll give you a homework as a one matrix. Okay, some matrix, maybe 3 by 3. You have to use Gauss elimination. You have to use Tdma. You have to use Gauss Seidel. You have to use Jacobi. Okay, these are iterative methods. Gauss Seidel, SOR. This also use. Here I will give you initial conditions. Okay, guess values, initial guess values. Here initial guess values are not needed. So you try this. Okay. So once you know how to solve this 3 by 3, by calculator, do this by calculator. First you do this assignment by calculator, and then in the next classes we'll see the algorithm of Tdma, computer algorithm, and you will be given an assignment based on this. Assignment number 1 will be to solve any problem using Tdma algorithm. This is your homework, and this will be your assignment. Okay.